Alright, so problem 2, a conservation of L problem. A person of mass m stands on a spinning flywheel platform, which by itself has a moment of inertia, I subscript p. Initially, the person is at a distance r1 from the center of the platform, and the platform spins with angular velocity, omega subscript 1. Then the person walks outward and stands at a greater distance r2 from the center of the platform. Solve for the final angular velocity, omega 2, of the platform in terms of the given variables. Is the final angular velocity greater or less than the initial angular velocity? Okay, so I started here with to kind of help the visual process with a little cartoon of first the person on the spinning flywheel closer to the center, and then as the person moves further from the center. And what we're looking for is the final angular velocity. Okay, so the first part of this is actually finding the angular velocity itself. So what I did here is I write down some equations that I think might help me. We have I equals mr squared, L equals I omega, and then another one that and then L equals mr squared omega, which is gonna help us answer also the second part of the problem. Okay, so what we do here is we have the moment of inertia I subscript p. So I have I subscript p equals m times r1 squared, r1 being this distance. And then I also have I2 equals mr2 squared. And since I have conservation of L, since I have conservation of L, and my omega or angular velocity is going to be changing, my inertia will be proportional. Will change proportionally to my omega, angular velocity. So what I have here is I have, since we have conservation of L, I can set I subscript p times omega 1, which is the angular momentum here, and then I can set that equal to m r2 squared omega 2, and omega 2 is going to be our final angular velocity, and then it only asks me to solve in terms of given variables, so I do some division and I come up with my answer right here for omega 2, and that is the final angular velocity of the platform in terms of given variables. And then the question asks, is the final angular velocity greater or less than the initial angular velocity? So, again, to answer this question, I can go back to one of the very first things that I'm given is conservation of L. So, given L equals mr squared omega, I know that omega will be, since r is increasing, and m is remaining constant, and L is staying constant, I know that omega will be decreasing because it's going to have to change proportionally to the radius. So therefore, I can assert that the final angular velocity is less than the initial angular velocity. something that really helped me solve this problem was to draw this. You should do it for every problem you do in physics, but specifically for this one. Another thing that helped me, also specifically for this problem, is to write out all these equations, even if I wasn't sure I would need all of them. That did really help me a lot. So yeah, those are two ways that students could avoid getting points off on this problem or even failing to understand it from the beginning. So yeah.